Hello everyone, good to see you. Okay, so let's just double check this thing works. Sorry about the delay. Let's see. So if everyone can hear me, could you please just wave and then we'll know that the latency is in. Yes, okay, let's go ahead and start. Okay, well, great. I hope everyone had a good weekend. It's getting warmer all of a sudden now, and I guess that means that the semester is almost over. It's really nice to be able to see all of you guys in this class anyway, though. So today I want to talk about another question, which at first looks like it might not have that much to do with sets, although in fact the kinds of thoughts that we'll use to solve this problem are the same kinds of thoughts that we've been using to solve lots of these other problems that have something to do with sets. The question is going to look just like a very simple graph theory statement, and this is a very famous theorem. This theorem is actually called the friendship theorem, and it was made by three friends. Well, they are actually three friends, but it somehow is called friendship theorem because the proof is actually quite interesting, and it's one of these theorems that that doesn't actually have a very simple let's say nonlinear algebraic proof. And let me make sure I put the names right. There's Erdős and Renyi and Sós. So this is by Erdős, Renyi, and Sós. Okay? And it's a theorem about graphs. It just says, suppose you have a graph where I guess there's at least one vertex, but for every two vertices, they have exactly one common neighbor. So if you're given any graph in which number of vertices is at least 2 and every pair of vertices has a common neighbor, has exactly one common neighbor, what can we say? I don't want to tell you what the theorem says yet. Let's try to figure this out. So this is a very, very simple statement. It just says that the graph has every pair of vertices with exactly one common neighbor. And why we put that there's at least two vertices is just so you don't have anything dumb. So we don't want it that there's only one vertex and therefore every two something happened because there are no two anyway to speak of. Okay, so if this is the case, what could we possibly say? Does anyone have any thoughts on what this graph might look like? I want to make some kind of a conclusion. So I haven't told you the conclusion, and let's just start to think. Can anyone think of a graph with this property? So before we continue, let's just write. Before I state the theorem, let's say some constructions. Can anyone think of any constructions? Liam. Okay, that's one. We could do a triangle. Every two have one common neighbor. Any other constructions? Philip. A projective plane again. So now we're going to be careful about what you mean by projective plane. One thing you could do is you could say, let's take a projective plane. There shouldn't be a dot here. Projective plane, and I guess we'll split it into the points and the lines, right? So we have some points, and we have some lines. And somehow what we do is we connect 2 if the point is inside the line. But I think if we drew just like this doesn't quite cut it, because if I take any 2 points, they have exactly one common neighbor. Any 2 lines, they have exactly one common point. But if I take a point and a line, then I don't have a common. So maybe I can't do quite this way. As you remember, we did something else called the polarity graph of a projective plane. There was something else that we had done. Actually, not the polarity graph of a projective plane, but we did something where we took like vector spaces over three-dimensional, like a field, three-dimensional vector spaces over a finite field. We could try a polarity graph. So this one I'll write question mark because there's an issue on this one because if I take a point and a line, that won't work. Polarity graph we could try. Polarity graph is somehow where every vertex is a one-dimensional subspace. of FQ3. So they're one-dimensional subspaces of three-dimensional space, and I connect two of them if they are somehow orthogonal. So we had that before too. But if you remember, that one also was a little bit weird because we had some issue where in finite fields, vector spaces over finite fields, you could have self-orthogonal vectors. So if you remember this particular construction, it wasn't always true that for every two different one-dimensional spaces, that there was exactly one-dimensional space which was orthogonal to both. Because unfortunately, if these two if you had some self-orthogonal one-dimensional space, then bad things happened. So unfortunately, this one doesn't work either. The funny thing is it almost works. So somehow the projective plane bipartite version almost works except for like the things which are on opposite sides. The polarity graph even more almost works, except it breaks on very special cases where there are some self-orthogonal one-dimensional subspaces. Any other constructions? So far we have one working construction which has three vertices. Hopefully this problem has constructions which have more than three vertices too.
Lots of triangles.
Okay, thank you. So there's another one which I could do with lots of triangles. And I think what you mean is this kind of lots of triangles. So here I have lots of triangles and they all share one vertex. Now why this one works is because if you look at it, if I have any two, if I have any 2 points, any two vertices which are not the center, any two vertices which are not the center, they have exactly one common neighbor, which is the center. And if I take any vertex and the center, there's exactly one common neighbor, which is the thing on this triangle. So I could do this, and I could do more triangles if I wish. I could just keep adding triangles. They would just all look like this. Okay, so that's another construction, and we could get arbitrary odd numbers of vertices that way. Any other constructions? Well, the answer is actually no. There are no other constructions. It's quite neat. The answer is, if you have this property, it looks like this. This is the only thing you can have. It's just a bunch of triangles that all touch at one vertex. So somehow, if given all of this, then the graph is this. Just that picture. Okay, so that seems kind of interesting. Somehow this condition here doesn't seem, at the beginning, doesn't seem so strong as to lock you down onto a very particular type of graph, but it does. So now let's attempt to prove this. So if you want to prove a statement like this, at the beginning it looks like a statement like this should be provable just by, I guess, bare hands, brute force, do some kind of induction. But it turns out that that's not so efficient and not so effective. It turns out that the best way to look at this is through an idea which is based on all the linear algebra that we've been playing so far. And how could linear algebra have anything to do with something like this? Does anyone have an idea of what I might be able to do with linear algebra? Is that somehow I have a situation here where I have to be talking about, every two vertices have exactly one common neighbor. What part of linear algebra or things about graphs could I use that? What could I use? First of all, what kind of tool should I use? I mean, I'm going to use linear algebra. I have a graph, so I suppose I should make a matrix, right? I should make an adjacency matrix. Let's go ahead and start with that. So we're going to do the proof. The proof is the rest of this. And so what we should do first is we should just first construct the adjacency matrix. Let A be the adjacency matrix of the graph. Okay, so now this adjacency matrix, it happens to be n by n. Because I guess there are n vertices. I should probably have said that from the beginning. So you have n vertices, and in this adjacency matrix, we just go and see, is one particular vertex adjacent to another one or not? It has some ones, it has some zeros. It's going to be symmetrical. It looks something like this. It has a 0 over here, it has a 0 over there. So this is our adjacency matrix of the graph. Can anyone think of how we can try to encode this information about every two vertices have one common neighbor? Ariel.
So you'd want to take dot products. So if you E transpose times A.
Oh, okay. So that's pretty interesting. So you're thinking of like dot products, which that actually works quite well. That's a great way to think of this, right? So if I look at these, I like how you said that. That was not what I was planning to say, but in fact, I think that what you said is even more intuitive. So let's use what you said. So the way to think of this is that, look, an adjacency matrix is just a bunch of vectors. And the vectors are these characteristic vectors. They're the 1, 0 vectors, which say which other vertices are you adjacent to. Okay, so let's look at the adjacency matrix like that. So the columns are these indicator vectors of which other vertices are adjacent. Okay, so that's perfect, because then the way we think of this is we say, if I want to know if two vertices have a common neighbor, then that's an intersection. That's an intersection of the sets of your neighbors. Perfect, that's where the dot product comes in. So the second key observation is that the dot product of columns is equal to the size of the intersection of neighborhoods. Now, if that's the case, then I should just take A transpose times A. Is that A transpose times A, or is it A times A transpose? Yeah, A transpose times A. I want that. So this is A. And what I should do is I should take A transpose times A, and that's going to be a matrix which is going to take all of these inner products, putting all these dot products together. And if I look at any particular position, if I look at what's going on in one particular place, the number in a particular place is exactly how many common neighbors does that vertex corresponding to the column and the vertex corresponding to the row have. That's exactly what this is. So this is going to be a number, and this is going to be the number of common neighbors of the row and the column. Okay? So that's what we're measuring here. And so if you look at this particular matrix, A transpose times A, that's quite nice. I actually know a lot about this. In fact, the condition was that all of these pairs have common neighbors, have one common neighbor. So then the A transpose times A should just be a whole bunch of ones, right? And by the way, A transpose is the same as A. Adjacency matrices are symmetrical. So in fact, A transpose times A is the same as A squared. Okay? And A transpose times A better have lots and lots of ones in it. So let's erase this question mark. I know what it is. Ones. Everywhere. Really everywhere? Well, almost everywhere. What do I mean by almost? What's the only place that I don't quite know if there are ones? Faye. Diagonal. I saw the hand motion, right? So the diagonal. So the issue is that on the diagonal, that's going to be the vector dot product with itself. So in fact, this is a very useful fact about adjacency matrices of graphs. If you take the square of an adjacency matrix, what you're going to get is you're actually recording the number of walks of length 2 that go from the row to the column. That's actually what this is all doing. Why I said that is because if you take adjacency matrices to other powers, that's also what you're picking up. But generally speaking, when you take a power of the adjacency matrix, you're going to find out how many walks of that particular power length are there that go from one of those spots to the other. Like adjacency matrix to the power 1 is walks of length 1. And that makes sense. Is there a 1 or a 0? It's like, is there a way to walk in one step to get from the row to that column? Okay, so then we got these walks. And that's also why the things that go along the diagonal are exactly going to be the degrees of the vertices, because that's the number of ways to get a walk of length 2, which goes from a vertex back to itself. It's basically the degree. That's how many ways to do it. So the only thing that's different here is that the stuff on the diagonal we don't quite know. But the stuff on the diagonal, these are the degrees. Okay, so now the proof of the friendship theorem basically proceeds by trying to say, if I have a situation that looks like this, then what could I say about the, what could I say to show that the matrix A has to actually be this very nice matrix which was all of these triangles in the first place? Now to do that, we actually need to go and do some graph theory. So the rest of this becomes a mix between normal graph theory and some linear algebra or thinking about matrices. And whenever you see a condition like a squared equals this, the thing that should go through your head is, that looks so special. It's like, how could you even be so lucky to get an a squared equals to that? That's too structured of a matrix. And once you realize that that's the way of thinking, what you want to do is you want to say, let's try to do a proof by contradiction. Let's try to say, we'll do one case first, and in that one case we'll find the construction with all the triangles, and then we'll assume for the sake of contradiction, it's not that. And if we assume it's not that, we just want to show that this can't be done. So that's the architecture of the proof. So then the first thing has to be, is there some simple condition that we can put on our graph which will let us immediately know that it's all triangles? And it turns out that the simple condition is a really simple one. It's called, does there exist a vertex which is adjacent to every other vertex? So we'll split into two cases. Case 1. There exists a vertex adjacent to all others. What does this look like? Then there's a vertex which is adjacent to all others. So once you draw something like this, maybe let's make the parity right. So we make a vertex which is adjacent to all others. Once you draw this, you say the condition forces that for every two vertices, there's exactly one common neighbor. So just go and pick the center and one of the other vertices. And when you pick the center and one of the other vertices, it forces you to go and find another one of those vertices to connect with. Again, because the center is connected to everyone. The center is adjacent to everyone. So my observation was, pick the center and any other vertex. And that automatically gives you one common neighbor. Must have one common neighbor. Exactly one. Exactly one common neighbor, and then that's just what you pick up. And if you do this, you can just do this over and over again. Because, for example, when I go and take that vertex that I paired with and the center, I already know my common neighbor. That's this one over here. So there's no more need to do anything with these two. These two little vertices which are off on the edge, they're fully satisfied, and I cannot connect anything else with them either. Well, actually, that's not... is that clear? We'll find out very soon. But let's just keep going along. It's like, do the same somewhere else. And if you do the same somewhere else, you have to have someone else who's adjacent to you, because you take it and also the center. Of course, I'm drawing it to the one that's right next to it, but in graph theory, it doesn't matter how you lay out the vertices anyway. You start going around, and you find out that you must match them up like this. But once you've matched them up like this, there's nothing else you can do. Because if you go and look at this picture, you take any two vertices, which are not the center, and they already have one common neighbor. And you take any two vertices, which is something and the center, and they also already have one common neighbor. You cannot add anything else. So that's a proof that if I have one vertex which is adjacent to all others, that's it. It's over. Okay. So that's case 1. And then case 2 turns out to be all we need. With case 2, we just want to go and get a contradiction. Case 2, that'll be the rest of the proof. No vertex is adjacent to all others. In this case, now we need to try to find out more. Now, the funny thing about this case too is it can't happen. So, I mean, somehow we already know that this is the construction. Now we have a funny situation where we're going to say, well, if this is true, then we're going to have some weird situation, and we'll use the weird situation to get a contradiction. And it's very hard to tell people like, oh yeah, surely that would be the weird situation that you'd have, because it doesn't happen anyway. However, if you use this condition, you can start to notice some interesting stuff. So we are now going to start from a nonsense condition and derive more nonsense stuff. So we're going to use that there's no vertex adjacent to all others, and let's get a new screen. Let's assume no vertex adjacent to all others. Now let's start to look at what everything has to actually look like. Here's a vertex B. B has some neighbors. I'll draw a better loop. Neighbors. Okay, so this is the neighbors of V. By the way, I have to have at least one neighbor, because otherwise there's no way that V and someone else could have a common neighbor, right? So that has to be the situation. And V has some neighbors. There will also be some other vertices out there. I mean, there will be some other vertex, which is, because I know no vertex is adjacent to all the others, I know there has to exist another vertex out here, which maybe I can call W. Maybe let's call that U, actually. U. And U happens to be not adjacent to V. So my little squiggle just means adjacent. The slash through it means not. So this is just not adjacent. Okay. And I have all of these vertices here, which are neighbors of V. Okay. Now I want to start to make some observations about what has to be true. We have to use the conditions. And the conditions told us that for every two vertices, there has to be a common neighbor. So what would be good to use? Anyone have a suggestion of what we could try to use? I mean, there aren't that many choices. I have this picture here, and I'm saying, let's go and find that let's use the fact that for any two vertices, there has to be a common neighbor, and exactly one common neighbor. Which two might be good to start with? U and V is one, right? So if U and V have a common neighbor, I already know for sure then, because U and V have a common neighbor, that common neighbor has to be in this neighborhood. And I'm going to write that down here. There exists a common neighbor inside here. Okay? So there exists exactly one such thing. I'll write exists unique common neighbor. There exists a unique edge from U into this neighborhood of V. So that's true, and that's one thing I can do. But I want to get more control on the graph. And maybe to give you an idea of what I mean by more control on the graph, let's go back to the statement that we need to play with. We ultimately need to do something with this a squared. And this a squared has something to do with the degrees on the middle. So I need to have some control of the degrees, perhaps, in order to be able to get some kind of contradiction. Because you see, if I just have a statement that says a squared equals this, and this matrix has like a lot of freedom still on the degree diagonal, then maybe it is possible. But what I'm giving a hint on is I want to do something about degrees. I want to make a statement about degrees. Does anyone have, and by the way, what you said, Ariel, is useful. We will use this piece. Anything else we can use? Like, I want to know, like, some other pair of vertices that's supposed to have one common neighbor. There's no real wrong answers here. It's just like, what else could I use? Two vertices, exactly one common neighbor. Liam.
V and something in the neighborhood of V.
Let's try that. So V and something in the neighborhood of V. So if I do that, there has to be exactly one common neighbor like this. Okay? So I have to, if I take one of these things in the neighborhood of V, there's one common neighbor there. Oh, but let's do it again. So I'll use another color. There has to be some common neighbor of this. Could they be the same? That's an important question. You know, I just drew these two, like two completely disjoint paths, the yellow and the green. Can they actually be the same? Could it have been that these vertices that are the common neighbor are actually the same common neighbor? What do you think?
No, they can't.
And they can't, because otherwise you'd have that two vertices.
Otherwise, you would have multiple
Right? You are not allowed to have two vertices here who have a common neighbor called V and another common neighbor which is out here. The two vertices are only allowed to have one common neighbor. So that's how I know that the yellow and the green are actually different, like completely vertex disjoint paths out here in the middle. Or else I would have two vertices in the neighborhood which have two common neighbors, V and the other one. So that's important. Maybe I'll make that comment. The green path and the yellow use distinct intermediate vertices. Since otherwise you have at least two common neighbors of their endpoints in the neighborhood of V. So I can't do that. Okay, so now I've got these disjoint things. Actually, let's keep going. So if I keep going, I'll find out that each of those disjoint, and maybe this one has also disjoint. So what? Can anyone tell me why this is interesting? This is a very powerful picture, what has just been drawn. Why is this interesting? Oh, wait, I should have made something clear. These things which are outside are also allowed. This doesn't necessarily mean that it's outside of the NV. This thing could actually be inside the NV. Maybe I should emphasize that, because I even know that the V is supposed to be, there's a unique neighbor in there. So in fact, the last one might look something like this. Does that make sense? Because this particular vertex, which is the last one, maybe its path of length 2, or the one common neighbor back to the U, that one might actually use that unique vertex which is up here, which goes through. Did that make sense? Like, we actually have to be aware that these things which are, that I drew outside here could actually have been inside the N of V itself. And in fact, there might be more of those, which are like routing inside the N of V. Oh wait, no, there aren't. Well, do I know that there aren't? Maybe I don't know yet. Maybe I could try to prove that there aren't. In fact, I probably could prove that there aren't. Yeah, Philip, I see you have a hand.
Yeah, there can't be more, because if you had, so they would have to all go to the purple vertex, and then if you had multiples going to the purple vertex, that would give you two distinct common neighbors.
Yes, exactly. So exactly, if you did that, then you would have the two vertices which have two common neighbors, at least two common neighbors. So it really looks something like this. Okay, so now why do I care about this? Can anyone tell me anything interesting that has to do with degrees, based on this observation alone? Ariel?
U has at least the degree of V.
Right? So what I just found out is, so when you have that there is a U which is not adjacent to V, you must have that the degree of U is at least the degree of V. Whenever you see a statement like that, that's a very powerful statement, because there's symmetry. When U is not adjacent to V, V is not adjacent to U. And whenever you have this inequality in one direction, but you're allowed to flip the U and the V, the inequality turns into equality, which is extremely powerful, and that's actually where this is trying to go. So now this thing works the other way around. By symmetry, also, V is then not adjacent to U, so that implies that the degree of V bigger equal degree of U, so they're equal. Degree of U is equal to degree of V. So now I have this statement that says, whenever I have two non-adjacent vertices, they have the same degree. This should make you very greedy. The moment you find out any statement that says non-adjacent vertices implies same degree, your greediness should say, let me prove that all the vertices have the same degree. That would be ideal. So how would I go about doing that? If I want to prove that all the vertices have the same degree, I need some kind of contagion to spread. It's basically that, at the beginning, there's a vertex V. It's not adjacent to everyone. That's how I know there's a U. So now I know that this V and that U have the same degree. And maybe I'll highlight that with some kind of a color. I'll use green. These two are known to have the same degree because U must exist. Okay? So now we're going to just talk through how this could happen. So I have that this V and that U, those are non-adjacent. There we go. Now we have all of these, those two which are the same degree. Now what else do I also know has to have the same degree? I just have to find things which are not adjacent to something which is already circled. Right? As long as I find another vertex and I can be like, I know that that's not adjacent, then I know I can circle it also. And that's where this unique is useful. That's why Ariel's original comment about there exists this unique edge which goes from U into the neighborhood of V. Since there's that unique edge, if I look at any of the other vertices in neighborhood of V, those are all going to be non-adjacent to the U. Is that okay? Actually, I should also say, wait, no, maybe let me draw a new picture first, because the new picture is going to be important. The new picture will take into account that there are more vertices that I didn't actually draw in this picture. Let's go here. Whenever we have these situations about paths of length 2 or distance 2, the most convenient kind of picture to draw actually looks like this. This is vertices, this is neighbors of the vertices. And then it turns out that every other vertex in the graph is actually reachable. Is actually reachable from there because everything has a path of length at most 2. But I don't actually need that fact. I'll just say everything out here is just not adjacent to V. Then I have all of these things here which are not adjacent to V, and also not V itself. And there's a bunch of these. One of them was U, but there's some more. And just to draw the graph that we had, there was this one exists unique. That was the one that Ariel's comment brought up. There exists one unique edge which is going there. And what we were just doing is we were circling the vertices which have the same degree. And in fact, I can circle everything out here which is not a neighbor of V, because, well, with V and it, obviously, because of my condition before, then they have to have the same degree. Now we'll also use Ariel's comment, and this U, I can circle every vertex of here, which is not that one that I picked. Not that one which is the unique neighbor inside N of V. Does this make sense? So it's sort of like contagiously spreading. The V let me circle all of these on the right column. The U let me circle everything here except that one. How do I circle that last one? That would be all I need. How can I go and claim that that one is not adjacent to someone? Well, that was the condition. I mean, this is probably too easy for you guys to want to answer. It's like the condition we started with was we were trying to, this is the case where no vertex is adjacent to everyone. And so it couldn't be that that one that's left is adjacent to everyone, or else I'm not in case 2 anyway, right? Case 2 was that for every vertex, there's going to be someone that you're not adjacent to. And that's how I get to circle the last one. So for the last one, the last vertex can't be adjacent to everyone, so has the same degree 2. Okay, so now we have this powerful statement. The powerful statement says, in the second case, we actually have no vertex is adjacent to everyone, and furthermore, all of the degrees are the same. Maybe let's give a name for that. Let's assume that that degree is k. So now, all degrees are equal to k. And going back into that adjacency matrix, we have that A squared is supposed to be this matrix, which has k's on the diagonal, because what we put is the degree of the vertex on the diagonal, and 1's off the diagonal. Okay, so that's going to be our square of the adjacency matrix. And by the way, we know something about k, because we know that k cannot be all of the degrees. There's no vertex adjacent to everyone. And so the k is actually less than or equal to n minus 2. We may or may not use that. We may or may not use that later. So this k is, it cannot be adjacent to everyone. Now we need to find a contradiction. And you need to say, come on, there's no matrix A which could possibly square to this beautiful thing. Now, if you're going to talk about the square of a matrix, it turns out that there's something in linear algebra which is quite nice to play with. Do you know anything that's useful when you take powers of matrices? Any concept in linear algebra that might be handy? Leah. Determinant is useful. The determinant of a square is the product, is the square of the determinants. The determinant of a square is the square of the determinant. That is true. I could do that, but I don't want to take the determinant of this. That wouldn't look like too much fun. I guess I probably could do it. Actually, you know what? We will know the determinant by the time we're done with this, but we'll know it because of another reason. And that's giving a hint. It's like I actually have a way to compute this determinant, which is not going to be as painful as multiplying everything out. Does anyone know anything else that's relevant when you take powers of matrices? And the hint is like somehow I'm telling you I could figure out the determinant. The determinant, by the way, there are multiple formulas for the determinant. One would involve Gaussian elimination. I don't intend to do that. One would involve multiplying all the things out. I also don't intend to do that. I mean, multiplying things out and adding them. That's no fun. But there's something else you can use to get the determinant also. Yes, Tingwei. Eigenvectors, eigenvalues, yes. So now we are lucky that A is a adjacency matrix. A is a real symmetric matrix. It's actually fully diagonalizable. But you don't even need that fact. Whenever I have any matrix, the eigenvalues of the square of the matrix are the squares of the eigenvalues of the original matrix. That's a useful fact. And the way that, I mean, why that's true, there are multiple ways to see why that's true. One way is to use this thing called Jordan canonical form. And if you take Jordan canonical form, you have these Jordan blocks, and when you square that, you will of course get the squares along the diagonal. And another way, if you just want to quickly see why this would work for fully diagonalizable matrices, if you have a complete basis of eigenvectors, I mean, if you just see that if I happen to have A times B is equal to lambda V, then of course A times B, let me write that better, then A times B is just going to be A times lambda V, which is just lambda times AV. Remember, lambda is a scalar, A is a matrix, and so that's just lambda squared V. So if you actually are lucky, if you're actually lucky enough to go and get a complete basis of eigenvectors, you could do this. If you don't, you can use Jordan canonical form, and when you square Jordan block, all of those diagonal entries square. Okay. But so that means that the eigenvalues of A squared are going to be exactly the squares of the eigenvalues of A. And by the way, A actually is a diagonalizable matrix. A is a real symmetrical matrix. So A actually has, A has all of these, actually has this full eigenbasis. So what we'll say is that the eigenvalues of A and then squared are the eigenvalues of A squared. And there's even a correspondence. It's that for every one of these eigenvalues of A, I can square it and get an eigenvalue of A squared. Why is that relevant? That's relevant because I can tell you what are the eigenvalues of A squared. How would you do that? So eigenvalues of A squared, what would you use? We could try to do this determinant thing where we take this thing minus lambda, and you could then try to calculate out a determinant that looks like this. But there's a better way. And the better way to find the eigenvalues of this kind of a matrix is actually to recognize that it's built from J. J was this all ones matrix. So now let's go and study the eigenvalues of A squared. Eigenvalues of, we'll have something here which has a lot of k's and a lot of 1s. This is equal to the J matrix plus k minus 1 times the identity matrix. Why is this relevant? Can anyone tell me how you could use this decomposition to hopefully find the eigenvalues? This is related to eigenvalues of matrix plus multiple of identity. Do you know what happens to the eigenvalues if I take a matrix and I add a multiple of the identity? Fei. Yes. If I have J plus K minus 1 times the identity, and I take that times some vector V, that's just going to be the old JV plus this K minus 1 times V. But if you were so lucky that that was actually an eigenvector with an eigenvalue of lambda, then this will just be lambda V plus K minus 1 times V, which is going to give you an eigenvalue lambda plus k minus 1. Okay, so if I do this sort of a thing, then indeed I can actually just go and find out what are these new eigenvalues. I just need to know the eigenvalues of j. How easy or hard is that? Well, the eigenvalues of j, it turns out that j is a rank 1 matrix. And a rank 1 matrix means that there's a null space of dimension n minus 1. And then, there's something else, right? And in particular, whenever there's a null space of dimension n minus 1, that tells me that 0 is an eigenvalue with multiplicity n minus 1. Because I'm actually going to be able to construct a complete eigenbasis, where for n minus 1 of those eigenvalues, I just use my basis for the null space. Because if I take anything in the null space and take j times it, I get 0 times the original vector. So this is a very important fact whenever you're doing this kind of linear algebra on matrices. What you can say is that the dimension of the null space of j is equal to n minus 1, because it's a rank 1 matrix. It's just this all ones and then repeated. And so what that means is that there's n minus 1 independent vectors such that j times v equals 0 times v. Perfect. So I've got n minus 1 of those already. Those are n minus 1 eigenvalues, which are all 0. And what else can I do? Can someone tell me an eigenvector for j? If I have an all ones matrix, what's an eigenvector for it, which has a different eigenvalue? Faye. I'm listening. Oh, Bryce. All ones vector. If I take j times the all ones vector, remember j was all one matrix, multiply by all ones vector, I'll get n times the all ones vector. So what I just found out is that the eigenvalues of j are 0, 0, 0, 0, 0, 0, 0, and also n. Okay, so now what I found out here is that this one has eigenvalues 0, 0, 0, and n. So if that's the case, then if I take them together, I just shift it all by... sorry? Oh, your video was lagged. I'm so sorry. Yeah. So you have to, I guess, refresh or something because of that buffering. I'm sorry about this. But no, so I got this piece, and I add the k minus 1. So if I add this together, I'll find out that the eigenvalues of this entire thing are k minus 1, k minus 1, k minus 1, and also n plus k minus 1. Okay? And how many of these are there? There are n minus 1 of these, and there's 1 of the other. Okay. Now, how could I try to go and get a contradiction out of this? Maybe I need to know something about n. How can I find n? Well, the good news is that you actually can write down exactly what n is in terms of k. You see, because I said every single vertex has degree k, but furthermore, actually every vertex you get to with a distance of 2. So let's now draw down the picture, which is the thing that I alluded to earlier. I've got this vertex. I've got its neighbors. And there's k of them. Right, there's k of them. There's one vertex here. And furthermore, every other vertex is going to have a path of length 2 to v. So in fact, every other vertex out here is going to be somehow adjacent to, well, actually exactly one of those vertices inside. Does that make sense? Every other vertex in the whole graph needs to have exactly one common neighbor with v. So it has to go in exactly once. And so every other vertex is going to do something like this. They all go to different ones. Furthermore, let's see. Can I have an edge inside here? Let's see. Would I be able to have an edge inside there? I hope not. It would be nicer if I can't. So let's see. If I put an edge inside there, then... Oh, no, maybe I do. the reason I say maybe I do is because for the vertex v and one of these here, it actually has to have one. It actually has to have one common neighbor. So somehow inside here, I also am going to have a matching constructed. Is this making sense to people? Is that somehow from the vertex v and one of these here, there has to be one common neighbor. That common neighbor must live in NV because that happens to be a neighbor of v. And so I have no choice but to actually pair these up. Okay, so my picture is going to look like this. And in fact, I don't have any more than that. Because if I, as a comment that Philip said, if I've got somehow two of these blue edges inside here, then there's going to be two vertices with one common neighbor up in NV and one common neighbor out in V. So in that case, I can count actually what is n. I mean, this is the graph, right? I mean, not that this is the graph, but these are all of the vertices. And in particular, each one of these yellow things going out, the number of yellow things going out is going to be k minus 2. And that's because I used one for the blue and one for this white. So there will be k minus 2 coming out of each one. So what that means is if I want to count all of these, it's just going to be k times k minus 2 are out here. So now let's add everything together. So I've got 1 plus k times k minus 2. If I add this all together, we're almost done. This is equal to 1 plus k times k minus 1, which is equal to k squared minus k plus 1. And that happens to be n, the number of vertices. Okay, so now that I have n is equal to k squared minus k plus 1, let's go back and see what I can do with my previous statement about these eigenvalues. So in these previous eigenvalue statements, the n I have here, n is k squared minus k plus 1. Oh, that's nice. K squared minus k plus 1, if I look at what happens with k squared minus k and then plus 1, actually this is just going to be k squared. Is that okay with people? That will be just plain k squared. And that's because of the fact that, well, I had k squared minus k plus 1, so that's over. And over here I have an n minus 1. Let's go and simplify the n minus 1. The n minus 1 is not n minus 1 because n is k squared minus k plus 1. So it's just k squared minus k. So I have these two. By the way, this should make you happy. The reason this should make you happy to see a k squared is because, remember, each of these is the square of an eigenvalue of a. And it turns out that if you have a regular graph, every regular graph, the adjacency matrix has one eigenvalue, which is the degree of every vertex. And the reason is because if you have a regular graph and you multiply by the all ones vector, what you pick up is just all the degrees. So it actually makes perfect sense that one of these is k squared. We're about to use that. Okay, so now what do we have? Let's summarize. What we have is that a squared has eigenvalues. There's a k squared, one of them, and there's a bunch of k squared minus k's. Now, in that case, I know something about A. So A has to have eigenvalues. This one better be a k, because as I said, you can take the adjacency matrix times all one vector, and when you multiply by all one's vector, you pick up all of the degrees. And since all the degrees are k, that's why I know it's not minus k. It's either plus or minus k. Philip, yes? That would be even better. Let's see. Oh, yes. Thank you. Much better. K minus 1. That would be better for what I need. So let's write k minus 1. Thank you. This is actually going to simplify what happens next. You see, what happens next is, where do they come from? Well, they have to be from eigenvalues of A and then squared. But I have two choices. It could either be plus or minus the square root of k minus 1. So some of them are plus and some of them are minus. Maybe some of them are plus square root of k minus 1, and some of them are minus the square root of k minus 1. Let's assume k is not like 0. That would be silly. If k is 0, there's nothing to do. Then A is a graph which has k equals 0 regularity. There's no edges. Clearly, it can be solved otherwise. And what we'll do is we'll say, let's suppose there's r of these and s of those. And by the way, the r plus s I have some control on, exactly as you've said. I made a mistake on writing that one, but r plus s, that was equal to the k squared minus k. Okay, so now I have this condition about A. Now I need to get a contradiction. And the way to get a contradiction out of this is another thing that maybe seems a little bit like cheating. There is one thing I know I can do with eigenvalues, which is I can add them up. And if you add up all the eigenvalues, you get the trace of the matrix. Why is that convenient for the trace of the adjacency matrix? What's the trace of A? 0. It's because it's zeros on the diagonal. So this is like, what? Okay, so at this point we just use whatever we know about matrices to go and try to get a contradiction. And the trace is the sum of the diagonal. Sum of the diagonal is 0. Therefore, the sum of all of this stuff has to be 0 because it's the sum of the eigenvalues being the same as the trace. So now what I use is that the trace of A equals 0 implies that if I have k plus r minus s times the square root of k minus 1, times the square root of k minus 1, that's supposed to be 0. Let's just go and move to the other side. So I get k is equal to s minus r times the square root of k minus 1. It's now time for some number theory. We'll just go and prove this is just not possible. Okay? If you have this, square both sides. Here are just some statements that are true. Square both sides. If I square both sides, then I find out that k squared is equal to s minus r, which is some integer squared, times k minus 1. This is telling you there's a divisibility. K minus 1 divides k squared. I mean, this is not what you expect in a combinatorics class, okay? But it works because we're in the last stages where you just go and beat up the matrices until you go and find out that, yes, there was a contradiction. K minus 1 is a factor of k squared. That's going to give us a contradiction. Because, you see, k minus 1 is a factor of k squared minus 1. It already is a factor of k squared minus 1 because of k minus 1 times k plus 1. So let me just finish it down over here. I know that k minus 1 divides k squared minus 1. But over here I just wrote that k minus 1 also divides k squared. Therefore, k minus 1 has to divide 1 because I just divided two consecutive integers. So we have this, and we also had k minus 1 divides k squared. These two combine to give you k minus 1 divides 1. And then that means that k has to be 2. Okay, if k is 2, what do I know? K equals 2, what was n? N was this k squared minus k plus 1. N equals k squared minus k plus 1. N equals 3. At this point, you can enumerate all graphs with 3 vertices, even if you wanted to. But if you just say, well, I've got a graph with 3 vertices and all the degrees are 2, that's a triangle. We already dealt with that case, so that's done. Right? We don't need to worry about that case. That's already a done case. And in every other case, so this would give me, actually what that would contradict is we assume that there was no vertex that was adjacent to everyone else. In a triangle it is. But this particular case gives us triangle. And that's okay. In every other case, we find a contradiction. And the contradiction tells us that you cannot have that a squared was this. Okay, and so that's the friendship theorem. And so this is a proof which kind of uses a bunch of these ideas we've talked about with, intersecting sets, dot products, multiplying matrices, and in the end we use this eigenvalues to finish it. Any questions? Faye, I see you have a question.
Is it still true if we allow and for the parallel edges?
Oh, is this still true if you allow self loops and parallel edges? I actually haven't thought about that. But if we think about what happens in the adjacency matrix, we wanted to make that there was 0 on the diagonal, and the 0 on the diagonal was very, very useful in getting this piece to be 0. So I'll say that the proof as stated wouldn't work. Oh, you know what? I wouldn't be surprised if I didn't check this, but I wouldn't be surprised if that polarity graph, if you allow to put a self loop when there's a vertex when there's a one-dimensional subspace which is orthogonal to itself, if you're allowed to put self loop there, I'm a little curious if that actually helps to give you a construction. You see, because we were basically doing something with regard to linear algebra. No guarantee, by the way, but my feeling is if you go and add self loops, maybe you can do something. Also, if I'm thinking about this, like with self loops basically give you the power to go and say, here are 2 vertices, and they didn't have a common neighbor, but they're adjacent already. And if they're already adjacent and don't have a common neighbor, you put this loop here, and then you Oh, but then you can screw up other ones. So, okay, I don't know. I was going to say maybe the self loop gives you a way to go and fix the problem that you have, but it's not clear that that actually works for me either. Other questions? Okay, well, if there are no other questions, I guess I'll see you all on Wednesday and enjoy the rest of your day. See you.